Okay, so I'll be back, lecture 9. We're continuing to learn techniques for writing proofs. Last time, I made a mistake, and I want to fix that mistake first before talking about the technique that we're going to do. So, we're going to write some example prove that if the b squared is even, then n. You have to remember the definitions that we covered last time, right? So just recall what it means. So even is the same thing as saying that there exists some integer k such that n is equal to k. And that's the definition of being even using logical quantifiers. Odd, same thing as there exists some integer k such that n is equal to 2 times k plus 1. And as I mentioned last class, don't get bogged down with k, use whatever variable you want. It doesn't matter. And also that integers are either even or odd. Okay. So when considering this statement here, we can translate it to a statement involving quantifiers and logic. So I can say, like, this is equivalent to saying that for all integers n, so n squared even implies that n is even. Right, so that's using universal quantifier on integers, right? So the mistake that I said, even though I could tell in my body language I was thinking the opposite, was the following. I said that if if this is false, then the statement's false. That's incorrect. If the hypothesis is false, the conditional statement is always true, right? So when considering this, right, we'll just make a point of it. This is true for all odd integers. Since the hypothesis would be false. Okay. So when the hypothesis is not satisfied, you'll hear me sometimes say vacuously true. And you might hear other math professors say that. So an example would be like, if that hypothesis could never be satisfied, then the statement is vacuously true. It doesn't quite fit here because the hypothesis could be true when precisely when n is even, when n squared is even. So yeah, gotta finish this sentence since the hypothesis would be false. And false implies anything is always true. Okay? So when considering that statement, we do not at all, like it's already true whenever n squared is odd. Or for all, wow, I really messed up this sentence. For all n squared odd. Okay. Okay. So we only have to consider the case when n squared is even. right? If we can show that that's true for n squared even, then it's done. It's all possible integers, right? Now, I don't want to spend too much time on it, but if you recall, this is the type of problem where we would want to do a proof by contraposition, right? Because if we started doing scratch work and we assume this hypothesis that the n squared is equal to 2k, and then we try to take like square roots, we wouldn't even know if we had an integer, it wouldn't work. So the contrapositive of that statement we need to consider. And the contrapositive is so for all n, there are integers. Not that implies not that. That's the contrapositive, right? So n not even is the same thing as saying n is odd, right? And then we're going to do the same thing here. N squared is odd. That's the negation of it. So now these are the same thing. That's equivalent to that. And again, just to re-emphasize what I said the mistake that I made last time and I get rid of it completely. To prove this, we only have to consider the case when what? That's true. Because if that's false, it's true by the definition of the conditional. Okay. So because I would like to get to the next proof technique, I'm going to just write out the proof rather quickly without the scratch word. And then we'll get back to the scratch word with the next proof technique. So I'm going to do a proof by contraposition or contrapositive. So I'm going to declare to the reader by way of contraposition suppose n is odd. So again, it's a descriptive sentence. It's telling the proof technique, which if they look at it, the statement, they take the contrapositive, it's that, and this assumption now makes sense. Because you're assuming this guy to be true. What's the next step? By definition. And it's like, so as soon as we declare something, we can typically make use of the definition to give us more information to work with. So then by definition, n is equal to 2 times k or some integer k. Honestly, I wouldn't be mad at you if you put k epsilon integer something. I get it. But I like to write things out a little bit more. Yes. Oh, +1. I left out the 1. Good catch. Which actually makes me happy because now these words like kind of fit in this little block. Okay, so after we make use of the definition, then we can do this next step. A little bit of algebra kind of things, right? So so then, and I use then right there. We can say like maybe like hence. It's a fancy word. Hence, now we're going to put our math like right here in the middle. What do we want to do? We want to consider what that implies about the square of n. And we're hoping that it's odd, right? So then let's consider that square. N squared is equal to 2 times k plus 1 all squared. Which is equal to 4k squared plus 4k plus 1. Does that look even? I mean, sorry, does that look odd? We can make it look odd. We can make it look like twice an integer plus 1, because that doesn't look like that right now. So we can do that by factoring out a 2. From the first two terms. So then we have to remind the reader of the definition of being odd, and we're pretty much done. We can say, since 2k squared plus 2k is an integer, n squared is odd by definition. And then finally, put your little QED box right there. Done. Okay. So before moving to the next proof technique, I think that we should do one more either direct proof or contrapositive proof together, where we're encountering maybe more than just one variable. And just to illustrate a point that I've seen, or like a mistake that I've seen happen a lot in my previous discrete math courses. So let's see if we can come up with a problem ourselves. Like, let's think of even and odd numbers and adding them together. Right, so if we have an even and an odd and we add them together, is there a chance it might be distinctly even or odd? So like 2 plus 3 is 5, so that's odd, right? Let's say 6 plus 3 is 9. It's odd. There's some evidence that maybe if you add an odd and even number together, it's what? Odd. We have 2 examples. So let's like consider this problem. We found the conjecture. The sum of an even integer with an odd integer is odd. That's the conjecture. Do you understand it? Like what it's trying to say? Now notice that it doesn't look like if then, right? But it's clearly either true or false. So it might help to translate this into a conditional statement using quantifiers if we want. Okay. So for the sake of brevity, I'm going to use quantifiers. So I like the letter n to denote an integer, so we're all n. And then we're all pick another letter. I heard it, I was waiting, so I heard either B or M. I heard M twice. Yeah, so maybe we use M. Like there's 2 variables now, right? We're summing 2 distinct things. I'm gonna run out of room. So I'm going to use brackets here. So n even and yes.
So since it's which were some 9 or so, seem to be percentage.
We're not there yet. These are just quantifying our domains of interest right now, right? So if we look at it, if we have any two integers and one is even and one is odd, then that's this, right? N even and M odd implies M plus N odd. That's the using our quantifiers and symbols to consider that, right? So it's as general as we want it to be, right? Recall that the conjunction doesn't matter the order, right? So it could be the first one's odd, the second one's even, doesn't matter, right? And if these are the same statements because it's for any n and n, right? Every single n that's even and every single n that's odd, it doesn't matter what combination, because that's the universal quantifier, right? It's the conjunction of all of those pairs. Anytime you satisfy this hypothesis, we're claiming that that thing is going to be odd. So yeah, I would think 21. It doesn't, or 11 plus 10, right? So let's go ahead and prove it. It happens to be true. And if you think about it, you can guess why. Can anyone guess why that's true? Like, why is that always true? That isn't clear to me. Not to like put you down or anything on this. I'm saying like it's not clear. Like what exactly does that mean? What about something like you're getting closer, much warmer. I was going to say something like some, an even, and an odd. The first number is even, the second number has an even part with a trailing one, or something like that, right? So two, like in this big sum, there's going to be three items. Twice an integer, twice another integer, plus one. So you can factor out a 2 from the first two, which twice an integer plus one, done. So that's why I believe it's true, but maybe after we write an actual proof, we can say it a better way. Okay? So here will be our formal proof right over here. And then I scratch work over here. And because of that intuition that we kind of gathered, I don't think like we can do this with a direct proof easily, right? So we're going to assume, what do I want to say? An even and M odd. Now remember, before I was going to discuss this example, I mentioned that there's something that I always see happen in my discrete math classes that goes wrong with these types of things. Keep that in the back here. So what's next? I make my assumption then what? Definition, right? So this is the scratch work. I don't have to like write it out. So what am I going to write here? Yeah, like the simplified version, right? So did you say n equals 2k? What else am I going to write? N is equal to 2k plus 1. All of you failed me. That's the problem right there. Why is this a problem? Yeah, like these are linking m and n together by k. Right? So like think about like if we assume that n is equal to 2k, right? Then an example would be like, so it's like 6, so k would be 3, right? 2 times 3, which would, so k is fixed at that point to the value of n. In fact, it's always one more than n with that choice of integer. we don't want them to be linked, right? Because again, with this universal quantifier, we want any combination of m and n. Like n could be 2 and m could be 1001. We want to prove for those cases too, not have them always, it's the same k. So we need a new k, like we need something else, like maybe q. Now they can vary. Does that make sense? So what we would have been proving if we stuck with what we had up there is that the sum of two consecutive numbers is odd. That's what we would have been proving. Now we're proving with that the sum of any even and any odd, any of them will be odd. So then we need some algebra now. And as we were kind of discussing, we can factor out a 2 from k and q. Twice and then e plus 1. So let's go ahead and prove it. I guess I can say something like, let n be an even integer. And m be an odd. And then, as before, use the definition. By definition, n is equal to 2 times k, and m is equal to 2 times q plus 1 for some integers k and q. Then we do our algebra. And n plus m is equal to 2k plus q plus 1. And we just factor out those twos. And then you can guess what's going to happen next. We just remind the reader of the definition. So since k plus q is an integer, n plus m is odd by definition. Okay, so I'm glad I went over that because I think like 98% of you in here said that there wasn't a problem. Not like it happens every semester, so don't feel bad. Okay. So next proof technique. So in general, you're proving statements of the form if P then Q, right? That's what we're doing. Even if it doesn't explicitly say if then, we can typically translate it to something like that. Okay. So one way of proving this, so we know something about propositions, like logical propositions and compound logical propositions. If the original statement is true, the negation is false. Okay? That goes both ways. If the negation is false, then the original statement must be true. So, proof by contradiction what do you want to do? So they go this proof by contradiction. Show the negation of if P then Q is false. If you can show the negation of the conditional statement is false, we know that the original statement is true. But there's this really important star, that's what I call it, identity, right, for conditional statements. Okay? This is going to be, so P implies Q is the same thing as saying not P or Q. And we want to show that to be false, right? From here to here is by that thing I call star. That logical equivalence. Now, if we, what am I going to do here? De Morgan's law, right? And for the sake of brevity, I'm not going to write out every single step. Negation, so we negate this. That becomes a conjunction, it's an and we negate that. So what this becomes is P and not Q. This is what we want to show. P and not Q is false. Okay. All right. Now, I think proofs by contradiction are best illustrated with, or at least like when you're learning them, I think they're best illustrated with proofs on rational numbers. Okay. So recall what it means to be rational. So the notation is this fancy Q. This is the set of all ratios A over B such that A and B are integers and B is not equal to 0. So if I can write you as A over B with non-zero denominator and A and B are integers, you are a rational number. So I'm just going to write out a conjecture. So maybe something like the sum of a rational and an irrational number is irrational. Maybe that'll be it. So, and again, for the sake of brevity, I'm just going to write out, like, I'll write it out nicely. So if X is rational and Y is irrational, then X plus Y is irrational. Meaning, if you're irrational, if you cannot be written as a ratio, it is non-zero denominator. Okay. So this looks like this. It's like logically equivalent to all x, all y, x in Q, and y not in Q. The in Q is just a set of rational numbers. Implies x plus y not in Q. Same statement. So if we assume a number is rational, we have a form to work with, right? But if we assume a number is irrational, what does that even, how can we write that? Right? There's no equation to write that with. Not that equations really matter that much, but for the techniques that we have, if we just assume only that and that, we don't have much to work with, right? We would have no idea how to add x with y because we don't even know what y looks like. So this is a prime example where we would do something like that, proof by contradiction. So the negation of this statement, so maybe I'll say like this. So we want to show that for all x, for all y, the hypothesis stays the same. You're going to see, so you want to look at P and not Q, right? So the hypothesis of the conditional stays the same. Then, and not this thing. So what's the negation of this? X plus y is rational. Okay. So that's what we're going to show. We want to show this to be false. That's the negation of that statement. So if this is false, the original one's true. So this is an indirect proof, just like proof by contraposition is indirect. We're using like logical identities to kind of trick our way into it. Okay. Here's our formal proof. Here's our scratch word. So we're going to prove by contradiction. Again, this is an indirect method, so we have to let the reader know what's going on. So on contradiction, we assume all of this. Now I want you to think about that for a brief second. In all of the previous two proof techniques, we assume like the hypothesis of some condition, right? Here, we're assuming that and something else. So it's almost like when you consider proof by contradiction, you get to assume more things and you have more to work with. So when I encounter problems that I have no idea what's going on, I typically start with thinking about proof by contradiction to get as much information in front of me as I need to try to figure out logically what's happening. If it's unnecessary to do proof by contradiction, I will realize it when I'm in there. I'll realize that I never needed to assume that, which is I can show that directly from this. And it's kind of, again, like back to like what I was saying about proofwriting last time, you want things to be as concise but clear as possible. If you include extra business, it doesn't need to be there. It's like jumbling stuff, right? So if you can prove it directly, do that. But contradiction is a great way to explore a problem. So let's go ahead and assume all the things. X is rational. Y is not rational. And x plus y is rational. Okay, that's assuming everything is ever. Now, the trick here is to get a fallacy, to get a contradiction. I remember the definition of a contradiction is it's a false propositional statement, right? So the way that this will occur, it can occur in many different ways, but for these types of problems, what's typically going to happen is that you're going to have something that you deduce using a definition, and something else that you deduce using a definition, and something that you assumed up top, where two of those things, and so like this and this and this, like two of those, one is true and one is false. They can't both be the same. And when you have a conjunction and one of them has to be false, it's all false. So, so what we're going to do is we have information about x and x plus y. So we can use the definition to say x is equal to a over b, where a and b are integers and b is not equal to 0. Again, this is scratch work. I can be messy if I want to. I don't encourage you to be messy, but you can. And then what else do I know? Can I apply a definition again? X plus y, right? It's rational too. So what does x plus y equal? It's rational, so then it's the same thing as x. There you go. C over D. Right? If you would have wrote a over b, y would have been 0. Right? It would have been forced to be 0. And a, b are integers, or no, sorry. C and D are integers, and D is not equal to 0. Don't forget that, by the way. If you don't state that those things are integers, and especially that the denominator is not 0, you could write a false proof. You could think that you proved it, but there's a mistake. Denominators, you have to be very clear that it's not 0. Okay. So, okay. So we could like, I don't know, how can we get a problem? Well, the only problem that could really occur is that y is not in there. Meaning that y, no matter how hard you try, you cannot write it as a ratio. What happens if you look at x plus y minus x? What is this equal? It's C over D minus A over B. Is this going to be a ratio if you combine these fractions? It's going to, yeah. This will end up being a ratio, which means that what? X minus x, that's just 0, right? What's left on this side? Y. Y is equal to whatever this ends up being. That's a contradiction. Because that means that it's rational and irrational. So I knew an old professor a long time ago that used to write this, like in his scratch work, to indicate he found the contradiction. And if you don't see it, it will become clear when I write it out formally. I'm getting jumbled over here, but it should make sense now. All right, here's the formal proof. So by way of contradiction, comma, suppose let's say x is rational y is irrational and x plus y is rational. Now, honestly, this might be a case where it'd be easier just to use the epsilon inclusion thing, but whatever, I already wrote. So, all right, now we apply the definition, just like before. We need something to work with. A definition. X is equal A over B. And X plus Y is equal to C over D for some A, B, C, comma, D that are integers. It's one way of writing it. For some A, B, C, and D that are integers, where B is not equal to 0 and D is not equal to 0. That's the definition of being rational, right? Here's a ratio of integers, non-zero denominator. Okay? Then X plus Y minus X is equal to D over D minus A over B. Right? The left-hand side of this equation becomes just Y, right? X minus X goes away. And then this side becomes what? B times C minus A times D all over B times D. You see that? I did skip a little algebra there, but it's just combining fractions. I multiplied the first ratio by B over B, which is just 1, nothing changes. Second ratio by D over D, 1, nothing changes. Then they have a common denominator, and you can combine them. Okay. So what do you think? Give me your best shot at it. What am I going to write next? Yeah, we could use therefore. I've been using since, but therefore is definitely a good one too. So maybe I'll help you out in this one because it is kind of different. By the way, did you notice my equations look a little bit different than my previous equations I've been writing? There's two sides to each of these dropping down, which that's when I use these double arrows to indicate that this equation follows completely from this equation. Okay, so let me finish this off now. So we can say now that maybe like note something. We want to get a problem. And the problem that I mentioned over there was that y is rational and y is irrational at the same time. That's the problem that we're seeking right now. So how is that going to be rational? Like, what does it mean to be rational? It can be expressed as a ratio of like something like an integer over an integer. Is that it? Right. B is not 0 and D is not 0, so the product can't be 0. There you go. That's what I was hoping for. Note B not equal to 0 and D not equal to 0, imply b times d is not equal to 0. Now, this is exactly where you would have run into a problem if you were happened to, there was like some condition on the rational number, right? There's some condition on it, and like you get to this point and you forgot to check that both of those weren't 0. Then you could run into a false proof. All right, so we have that. So then we can finish it off. Since E times C minus A times D, comma, E times D are integers, Y I want to make it nicer. I'm going to call this equation right here, I'm going to give it a label. Since those things are integers, that equation, capital E, sorry, implies Y is rational. I don't like it. I have to change it. I'm sorry. I was like, since that and didn't seem as clear as it should be, BD is not equal to 0. Equation 1 implies Y is rational. And then the last sentence would be this is a contradiction since Y is irrational. Done. And again, to emphasize that we haven't caught it yet, right here in our first assumption, the first thing we declared, Y is irrational. But if we assume that X is rational and we also assume that X plus Y is rational, if you're using definitions and this little bit of algebra, we get a problem. We get that Y must be rational in that case. That contradicts our original assumption that it was irrational. So the statement's false, which means that the original conjecture, where'd it go? It's gone. It must be true. Okay. So as you can tell, these take a little bit more words. It's a little bit more wording. And maybe even how much I'm writing is kind of overkill, but it's still, to me, it's clearer this way. Okay. So I would like for all of you to try to prove this conjecture and bring it to class next time, if you're coming to class. And I want you to not look it up or anything. You're not getting graded on it. And I don't even really want you to write your name on it. Just write it out as cleanly as possible. And I want to look at them next time. So again, it's a conjecture. So it's a similar conjecture to the one we just proved. So you have like a template almost. So if X is rational. And Y is irrational. Then X times Y is irrational. Yes. Well, the thing we just proved, this is different though, right? This is multiplication. Yeah, this was the sum of an irrational and irrational is irrational. That's what we just proved. This is a very similar conjecture. The only difference now is instead of adding that algebra, we're multiplying. Okay, so please write it on a piece of paper as cleanly as you think that you can do it. Like write it nice, like you're going to turn it in for a grade, even though I'm not going to grade it. You don't have to write your name on it. I just want examples of that there to talk about next class. All right, that'll be it for today. No scratch work, only the final proof. Okay. And thank y'all for coming, and I'll see y'all next time.